Okay, maybe we'll get started. So today it's a pleasure to have Zhaohuan Zhu from University of Nevada, Las Vegas. He got his bachelor's degree in 2005 from Peking University, and he did the thing which I always tell my undergrads to do, which is not just do applied math, not just do astronomy, but to do astronomy and applied math. Then he did his PhD at University of Michigan in 2011, working with Lee Hartman on Ephemerionous outbursts and protostellar disks. Then he was a Hubble Fellow at Princeton with Jim Stone, and then joined the faculty at UNLV in 2016. It was the Alfred P. Sloan Foundation 2017 and 2019. He was a co-PI at one of the NSF TCAN theory and computational networks for computational studies of planet formation. And he's done really beautiful work on a very wide range of things, from formation of planetary embryos and disk spirals and disks, to circumbinary disks, circumbinary planets, circumplanetary disks, mini disks in AGN, changing look AGN, magnetospheric accretion, X-ray binaries like dwarfs, young stars, and so on. Formation of binaries and AGN accretion disks and disk effects on their orbits, relevant to LIGO perhaps. Today he will tell us about some of those things, in particular the misaligned disks. So.
Yeah, thank you, Sterl. I'm not sure I have done all those things you mentioned, but today I'll talk about the companion disk interaction from small scales to big scales. Before my formal talk, first I want to explain the title. What is the companion disk interaction I mean here? So probably the most famous disk systems in astronomy is Saturn's ring. Right? We have this beautiful Saturn's ring made of these tiny particles from micron size to meter size. Spread a large area, but this ring is incredibly thin. This ring is less than 10 meters thick. So it's probably thinner like than this building, but it's spread along a large area. So this is a Saturn's ring, but if you look in detail, these rings have structures. Like here, you can see the moons in the Saturn's ring. And this is an 8-kilometer wide moon. Darkness, this gap is 42-kilometer wide. But because this moon has some inclination, so when the flow, the ring particles are moving across the moon, they will be excited, have vertical motions. Okay? So it will excite these vertical waves. And this image was taken at a time where the sun is shining from the edge. So it's almost perfectly edge on shining to the disk. So you could see these shadows. So then you could use these shadows and the geometry between the sun and the ring to estimate how high this wave is. So by studying these shadows, you know that, okay, this object is 8 kilometer wide, and then the waves actually goes to 1.5 kilometer high, although the ring itself is only 10 meters. So this is a huge wave in Saturn's ring. So here we have a companion of Saturn, which is the moon, and we have the disks around the Saturn. So here is a classical companion disk interaction picture. Okay. So if we go to higher, bigger scale, this is a protoplanetary disks around young star. These protoplanetary disks formed when the star formed. They are leftovers from star formation. We have dust and gas in these rings, and these dust will coagulate to form planetesimals and form planets like our Earth. We stand here, and it will also increase gas and form giant planets. Right? So this is the disk around the star. And in this particular system, people have found the two planets, B and C, in this cavity. And B and C are both Jupiter mass planets. And one is around 21 AU, this one from the star, and another is around 34 AU from the star. So AU is the distance between the Earth and the sun. Okay. So have two giant planets from far away from the central star. And the most remarkable thing about this system is the right image here. This is a radio image. So it probes dust particles in the disk. And you can see that there are dust particles around this planet. Okay. So this means it has a dusty circumplanetary disk. So moons could potentially form in these disks around this planet. So here you have like a disk, like ring, like this is a bigger version of Saturn's ring. So we could think about this is like a ring system in a ring, in a ring. So it's like another companion disk interaction problem. Okay, so now we have a bigger scale where we're looking at like the size of a solar system. So if we go even bigger scale, for example, oh no, before I show that, let me show rendering of that of a simulation we did for that PDA-70 system. So this rendering is made by the California Academy of Sciences. It's basically every snapshot in this movie is made from the numerical simulation we did for this particular system. So the reddish color thing here you see is this gaseous disk around the star, and the planets are formed in this disk. And the yellowish color thing here actually is the dust particles in the disks. So you have both dust and gas in the same system. The dust here will eventually could form planetesimals or planets, and you have two giant planets formed in these disks. One at 20 AU, one at 30 AU, and you have a circumplanetary disk around these planets. Okay, so you could also see there were like material at the L4 and L5 Lagrangian point. Some of these have been observed recently with the ALMA. So we have seen these systems as a disk system with a companion in the disks and interact with these disks. So if we look at a bigger scale, like AGN scale, we also have a disk companion systems. So you see this beautiful jet from Hubble image, and this jet is produced by accretion disks around the supermassive black hole at the center. So these disks accretes at very high rate and generate a lot of thermal energy or radiation energy. So you see it's a bright blob here, and most of the light actually comes from this accretion disk. The accretion disk luminosity outshines the whole galaxy luminosity. And this jet here is this jet, but with the Event Horizon telescope, we could actually see the inner edge of this disk. Okay, so the image you see here is the inner edge of this disk with a black hole at the center. You probably cannot see the scale here. This is a solar system. Pluto is here. So this black hole is larger than the whole solar system. So this is a like very big disk systems. And the supermassive black hole is like 6 billion solar mass. So we again have a disk systems. And the disk could have stars or black holes. So again, we could have a companion disk problem at a much bigger scale. So if we look at this AGN picture, the central mass black hole comes from millions to billions solar mass, while the companions in this AGN disk goes from 1 to 100 solar mass. So the mass ratio between the star and black holes in the AGN disk compared with the central star in the mass ratio around 1 billion to 1,000. Now, if you remember the protoplanetary disk picture we had before, the central object is the sun, the solar mass. And the planet mass comes from like Mercury's mass to Jupiter's mass. Then the mass ratio between the objects in the disk to the central objects is again around 1 million to 1,000. So just from this mass ratio perspective, these two systems have like overlapped range, mass range. Okay, so they should also share the same physics, which I'll talk about later. On the other hand, observationally, these two different systems are observed. You have different observation power for these two systems. For AGN disks, the disk is like parsec scale, while the AGN like M87 is a 10 megaparsec away. So the disk's size in the sky is only 0.02 arcsec, very small. So basically, we cannot actually see the disk unless you have Event Horizon telescope. For protoplanetary disks, on the other hand, the closest proto stars are 100 parsec away. The size of the disk is 100 AU. Then you have the scale of 1 arcsec. So you could comfortably resolve the protoplanetary disks. So because the physics between these two systems could be similar, by studying any of these, we may be able to get insight from this planet interaction problem and shed light to the other systems is harder to observe. Okay. So this is the companion disk systems across all the scales. They share a lot of similarities. So how the companion and the disk will interact? This theoretical problem has been studied over decades. So Frank Xu wrote a review. It's called the 6 Decades of Spiral Principle Theory. So it's a very extensive theory on companion disk interaction. And here I'll summarize it, or summarize with 2 movies. Okay. So in the first movie, we have a static fluid. It's like a water pump, a static fluid. And you are perturbing the fluid, like, for example, throwing a rock in the water pump. So what you will see that the waves will propagate like a ripples in the water pump. Right? So this is a density wave propagate in a static fluid. If you throw a rock, you have ripples propagate at some speed, or actually surface gravity wave speed. But for Keplerian rotating disk, so imagine now you are starting a whirlpool. The flows is orbiting around the central star at Keplerian speed, and you do the same experiment. You perturb the disk, and the perturbation will actually travel around the central object at Keplerian speed, and the perturbation will also try to propagate in and out. Similar to here, the propagation will propagate. The perturbation will propagate, but due to the Keplerian shear, the propagation when it travel inside, they will be sheared into a spiral wave. So overall, in a rotating disk system, if you have any perturbation, you will generate a spiral wave. So it's a spiral form. The waves propagating in the disk are always in the spiral form. So now if we replace this perturbation with a companion, like here, we have a companion. It could be a planet in a protoplanetary disk, or it could be a star in the AGN disks. This companion will excite the waves. And while the companion is orbiting around the central object, the waves will coherently add together. So eventually we'll form this nice single spiral arm. So we have observed these spiral arms at different scales. For example, at the protoplanetary disk scale, we see these 2 beautiful spiral arms with 1 system. And in much larger galactic scale, we have the whirlpool galaxy. You have a satellite galaxy inside these spirals. They're remarkably similar, although at dramatically different scales. This is hundreds of you, this is thousands of parsecs. So actually a while ago, motivated by the similarity between these 2 phenomena, we proposed that maybe we have a hidden planet here in this system inside these 2 spirals. And I was very encouraged by the recent paper claiming that they have found this hidden planet, but not connecting with this spiral, but connecting with this spiral. So our theory were not quite right, but the companion could be either way, could be here or here. On the other hand, by talking with Dimitri this morning, I am aware that this kind of observation is very challenging. So there are still a lot of things we need to know that to study to understand this is real perturber in the disks. Okay. Here the author claimed this is a Jupiter mass companion in the disk side in the 2 spirals. So these spirals are not only helpful for us to pinpoint the potential perturbers in the disks, they also lead to the perturbers migration. For example, the inner spiral will attract the companion, may accelerate, so the companion will gain angular momentum and move outwards, while the outer spiral will try to slow down the companion by gravitational pull. So the companion will lose angular momentum and move inwards. Because the global geometry, the slight imbalance between these 2 eventually leads to migration. Okay, so this is called the wave torque, and will lead to very fast migration. So this nice spiral only exists if you have a very circularly orbiting companion. On the other hand, if you have an eccentric companion, the picture is very, very different. Okay, so here are 2 movies. On the left is similar to the previous image. We have a circular orbiting companion, and we are in the rotating frame of the companion. So the companion is always here. On the right, we have an eccentric companion, and in the rotating frame of the planet, the companion will look like traveling left and right. Okay, so if we play the movie, you can see in the rotating frame, the planet inside these waves. And if it's a circular companion, the waves will coherently add together to form this nice spiral. But if it's a traveling planet in the disks, then the spiral wave is very different. Right? So you will continuously excite waves. They will propagate in the disk. They will interfere with other waves and form this very complicated pattern. This pattern also changes with time. Okay. So this is very similar to if you drive a boat in a water pump, right? So the wake you formed is not these squared ripples, these circled ripple anymore. You have a different shape. This is exactly the same mechanism. So we could make this analogy and build an analytical model to explain this spiral, how they will change with time. So potentially we could use this analytical tool to understand companion eccentricity disks. Encouragingly, there were some recent observations showing that these spiral systems in protoplanets are actually changed with time. And also the two spirals in this system are moved at different speed. They kind of move in the distance speed. So it may have some implications that it could have a companion, eccentric companion in the disks. So in future, when we have more and more of these observations, by studying how these patterns change, we'll be able to use these disk as a tool to do seismology. So it will be like a disk seismology to study companions' properties like mass, eccentricity, or orbit stuff. Okay. So far, I have shown you the companion, low mass companion in the disk will excite waves. What happens if you have a higher mass companion in the disk? If you have a higher mass companion, the waves excited by the companion will not steepen to shock. So it's the same as if you have like a drop a pebble, you excite these ripples. But if the pebble is huge, okay, or if there's an earthquake, then you have tsunamis, and then you will be breaking to a shock. And the shock could damage a lot of things. Like we know tsunamis could destroy a city. Right? So if you have a massive planet in the disks, these massive planets will excite this spiral shock. And this spiral shock will start to damage the region, co-orbital region of the planet, and expel the material in the co-orbital region away from the planet. In this case, for a higher mass planet, it will open a gap in the disks. And the gap edge could be unstable and form these vortices, non-asymmetric features. So overall, this picture of this companion disk interaction picture has been seen in observations. For example, we have seen this companion, these two companions open a cavity, like here. We have seen companions could drive spirals, and we have also seen disks which show these asymmetric features. So far, the theory seems to agree with observation relatively well. If you have like a coplanar companion orbiting at Kepler speed with the disks. So in the rest of my talk, I'll show that there are some more recent observations start to drive us to think one step further than previous simple companion disk interaction feature. Especially, there are observations to show that the protoplanetary disks, there are some disks that are misaligned. That requires us to have a misaligned companion in the disk. So now we have the companion not in the disk plane, but the misaligned. And this misaligned companion could do a lot of things. It could break the disks. And this could explain a lot of protoplanetary disk observations. And the disk will feed back to this companion and change the companion's orbits. And this may maybe apply to stars and black holes in AGN disks. So let's start with these new observations to drive these new theory development. So this is a disk around a binary star. It's a circumbinary disk. And you see this bright ring here. This is basically the cavity edge illuminated by the central star. So it's like a bright ring illuminated by the star. But on the other hand, you see these dark point in this ring. So somehow something blocked the starlight and causes these two dark points. So you could build a model to show that there is a 10 AU inner disk, which is 70-degree misaligned with the outer disks. And because the inner disk is misaligned with outer disks, the inner disk will block the central starlight at the node position. So at the node position, you will have disk shadows. And you can reproduce this observation very well using this model. So you clearly see the shadows here. So in this example, we have a disk. We have a small inner disk and a big outer disk. They are misaligned. So what causes the misalignment? And the misaligned disks not only have been seen around circumbinary disks, they have also been seen around the circumprimary disk. This is another example. You have a companion far away from the primary star. This companion drives these two nice spirals, as expected. But if you look at this ring in detail, there are also two dark gaps here. So these two dark gaps can be modeled with a 70-degree misaligned inner disks, and the inner disk cast shadows to an outer ring. So now you have these significantly misaligned. More puzzling, there are systems that you don't have any known companion and you still have this misaligned disk. For example, in this case, you see part of the disk, right side of this is dark, while the left side is bright. While the right side is dark, the inner rim seems to be bright. So to explain this observation, you only need like a mildly inclined, 30-degree inclined inner disk. The left side of the disk is fully illuminated by the central star, so it's bright. While the right side, the far away side, is blocked by the inner disk, while the region close to the inner cavity edge could be illuminated by the star, but coming from the bottom side of the inner disk. Okay, so this explains this asymmetric illuminated pattern. So this is a synthetic image from this model. You can see they agree fairly well. Okay. So here we have these misaligned disks. So what causes these misaligned disks? How you can generate disk breaking and make inner and outer disk misaligned. So the first way you could make the disk misaligned is that you have a misaligned companion. So let's start with a precision, disk precision. So if you have a spinning top, we know the top will precess right, around the direction of the gravity. Now imagine you have a disk. The disk is also rotating around the central star, apparently rotating disk around the central star. And then you have a companion. The companion is misaligned with the inner disk. The companion's angular momentum vector is this, while the disk angular momentum is pointing towards you. So the gravitational interaction between the companion and the disk will make the disk to precess counterclockwise. So this is an animation to show that if you have a companion here, the disk will start to precess. So now imagine you have a disk. Initially, it's not broken. It's not misaligned. It's a flat disk, but you have a companion misaligned with the disk. And this companion now could open a very wide gap in the disk. And this gap is important to stop the communication between the inner disk and the outer disk. So now the inner and outer disk do not communicate with each other, while the disk will precess by itself. And the disk precession speed depends on the disk size and disk surface density. So the inner and outer disk will just precess by themselves. And then if the inner disk precess like 180 degrees, there is a significant misalignment between inner and outer disks. Okay. So the question is, in order to do this, how massive this companion needs to be? Do you really need a binary star, or you could have a planet to cause a significant misalignment? So we carried out these simulations with the inclined planets using Athena plus fluid hydrodynamic code. So in the simulation setup, our planet is actually in the midplane, moving left and right, while the disk is initially misaligned. Yeah.
So in the previous picture, when the companion breaks the disk, does it also block the viscous accretion from the outer component?
Yeah. So you could have some flow passing through, but the gap cannot be very shallow, because then the sound wave could propagate through it and communicate. So yeah, so I'll show there is a condition that you have to, like, the gap depth needs to be deep enough to stop the sound wave communication. Yeah, so yeah, thanks. Yeah. So in a simulation, we cannot tilt, it's hard to tilt the planet, so we tilt the disk, okay. But here you can see the planet start to break the disks and the inner disk precess by itself. So here, this is an animation showing that if you have a planet in the disks, while the disk is very viscous, as you said, if the disk is very viscous, it means the disk has high viscosity or very turbulent, then the flow will pass through the gap and get to the inner part, and the gap cannot be opened. So when the gap cannot be opened, the inner and outer disk communicate with each other and will persist as one body. But if the disk viscosity is low or the turbulence is weak, then the companion will open a deep gap. And then the inner and outer disk do not communicate with each other. The inner disk just persists by itself. And then you cause a significant misalignment between inner and outer disks. Okay. So clearly this disk breaks depends on how deep the gap is. So when the gap is shallow, there is no break. When the gap is deep, you break. So you could work out analytical condition when that will happen. First, you could relate the planet mass and viscosity to the gap depth. And then the gap needs to be deep enough. So they satisfy this formula to stop the communication, the differential precession between inner and outer disks. So if you combine these two conditions, you could derive that the minimum mass to break a disk satisfy this formula. So for typical protoplanetary disk condition, that means it needs to be larger than Jupiter mass. The companion to central star mass needs to be larger than 1,000th. So it's Jupiter mass is 1,000th of star mass. So this tells us that in order to break the disk, as we've seen in previous these observations, we need a planet relatively massive, like Jupiter mass. So this also explains why these gaps, the shadows systems have only been observed when you have very wide gap, because you have very massive companion to open very wide gap. It also suggests that these disks with shadows could be prime target for searching for exoplanets, because they could harbor a very massive companion. So maybe we could search for exoplanets in these disks which show shadows. So these, if this mechanism really works, it also have observational predictions. When the inner disk precesses, then the shadows should also precess around the outer disks. In this animation, the inner disk has precessed for 60 degrees, while the shadow only changed for 30 degrees. So the shadow does not move at the same speed as inner disk. And this is a geometric effect. Just to show this, I made a toy model, use papers to show the inner disk and outer disk. And the inner disk will precess around this, my chopstick. And so if the precession is in this geometry, then when the inner disk precesses, the nodal position will circulating around the central star. Okay, so then the shadow will move at the same speed as the disk precessions. So they will move together. On the other hand, if the precession is like this, okay, if the precession angle is horizontally, while the inner disk precesses, the shadow will be always just librating over a small region. Okay. So the shadow's movement and the inner disk movements is complicated, right? You could work out the math formula, but overall, it tells us that by studying the shadows or the shadows movement, we'll be able to reveal the disk geometry between inner and outer disk. And if you get the precession speed of the inner disk, it may be able to constrain the companion mass. So there is a recent observation for TW Hydra. People have monitored these systems over decades, and you see some shadows. It's not very clear, but the shadows seems to like librate. So this is the best fit. So the shadow does not go through the 2 pi, and instead of like librating over azimuthal angles. So maybe this is one of the first evidence that we have seen these librating shadows or very misaligned inner disks, the outer disks. Okay. So I have described one mechanism to break the disks, but there are another way to break a disk is through the binary at the center if there is a binary system. Okay. So this is motivated by this system. So this system, TWORI, have 3 rings, and the innermost ring is circle. So clearly, you look at this ring face up, it's a circle. But the outer 2 rings are ellipse shape. It means they are like inclined. Right? So just based on the shape of the ring, you know the inner and outer disk is aligned. So one way you could do this is, okay, I have a companion between these 2 rings, and which break the disk, causes differential precession. But another way to do it is that you have a triple star at the center. This triple star, you have a closed binary and you have another binary further away. So it's a binary system. And this triple star could torque the inner disk and make the inner disk tilt. And eventually, if the tilt is strong enough, then the disk could break. Okay. So in here, in this scenario, you don't have any companion between these two rings. Just use the binary and the center, you could break the disk. So we studied this again using fluid hydrodynamic code. This is done with Ian Robaco, is a graduate student at UOB. He's an excellent student and he's graduating next year. So he's looking for postdoc positions. And we are studying the disks with the equal mass binary, but in the polar configuration. Overall, the disk will precess around the binary. So in the movie here, we have two movies. One is the case with a very high viscosity. One is a case with low viscosity. So with high viscosity, you can see that the inner disk is trying to precess. But very quickly, the inner disk align with the binary. And then it will develop a steady warp. And this warp will diffuse outwards like a diffusion equation describes. So the inner disk precess and then get aligned with the inner disk, and this warp will just propagate. So in this case, you don't have disk breaking at all. Things were smooth, although the inner and outer disk may not be like aligned, but there is a steady warp connecting them. But in this case, with low viscosity, then the inner disk, when it's precess around the eccentricity vector, they break free from the outer disk. And here you see significant misalignment between inner and outer disk. So you could estimate where this breaking radius is just by using timescale argument. Okay. So the inner disk, when you're trying to precess, you will transfer this information outwards with sound wave. Okay. But if the inner disk precess fast enough, the sound wave will not be able to reach outer disk, and the outer disk does not know the inner disk is precessing. So these will not communicate with each other, and then a break will happen. So you could calculate how fast the sound wave could propagate in the disk and how fast the disk will precess. And when these two time scale meet, it means that the communication time scale now is shorter than the precision time scale, then the disk cannot hold together, they'll have to break. So this simple theory predict that here you will have a breaking radii, and this simulation will show that indeed the disk break. Okay. So so we have this simple theory to explain disk breaking, and the precision time scale depends on the disk surface density profile, while the sound crossing time depends on temperature. Right, the sound crossing is basically sound wave, so it depends on temperature. The precision depends on how much mass in each ring, so it depends on the density. So you have these temperature changes with radius, density changes with radius, and you could do this parameter study to see under what condition the disk can break. Here, the disk break. So overall, the disk is easier to break with steeper temperature decrease or steeper density drop. So previous simulations here, the disk breaking too. But this theory also predicts that you could have scenarios of disk can break into multiple rings. So it works in this way, that you have the first break. After you have the first break, the outer disks will start to develop warp or start to precess. So you could calculate the time scale. And then when they meet again, they will break. They will have another break. Then the outer disk start as a new disk. And again, you have these two time scale. And so theoretically, you could have a disk with many, many breaks at the right parameter range. So we have the prediction that for a case here, the disk will break into 3 pieces. So we did one of the simulations with that parameter set up. And you clearly see the inner disk. Here is the binary at the center. The inner disk break free. And the outer disk start to warp. And the bodies have this steady warp connecting with the outer part. And eventually, this second disks like precess fast enough, and this warp start to break. And in these systems, you will have like one break here, and you have a second break. And in the simulation, it actually suggests there is a third break start to develop here. So in this case, at the right parameter, a single disk can break into many, many rings by the companion at the center. So here is another way to look at it. So if we divide this disk into a lot of rings, and we could calculate where the angular momentum vector of the ring is and project this angular momentum vector to the disks. So you could see that the inner disk precess very fast. Okay, now it breaks free. While this region between 5 and 15 start to precess. And there is a warp trying to connect them. But eventually, this warp is not strong enough to connect these two. And then it will break free. So when it breaks free, then this second ring will quickly be aligned because the sound wave in the ring will communicate the regions inside here. So they will quickly be aligned to form like a coplanar or one disk. Yeah.
What is the initial condition that you're?
Yeah. So the initial condition, the disk is just one flat disk, and the binary is like I think 60-degree misaligned. That's it. It's very simple.
It just appears as a disk.
Yeah. So that's an initial condition we said. Like we have a binary just in the disk, a flat disk. In reality, probably it's not that way, right? You form a binary at the center. Maybe you could have a latent four to form a secondary disk, which is not perfectly aligned with the binary. But the only requirement here is that the inner binary is not aligned with the disk. As long as the binary is not aligned with the disks, it will start to torque the disks. And for this particular setup, we need to use a very fast, relatively fast density and temperature slope. Like density need to changes like R to the -4, while temperature changes R minus like 3. Probably it's not realistic in protoplanetary disk, where the temperature you only change might be about like constant to R here. So that simulation has particular design to show this multiple break, but it may not happen in a real protoplanetary disk, but it could happen in other disks. For example, in some disk regions, you have dramatic temperature change or density change. This may happen. Or when the disk is very thin, like in AGN disks, this may happen. So yeah, so this is the only requirement is that the misaligned companion at the center. Oh, yeah.
So does self-gravity not save you once you go far enough?
Self-gravity?
Yeah, self-gravity from this, because that'll cause a retrograde precession that will detune the effect of the inner fighter.
Yeah. So in this simulation, we assume the disk mass is very low. So there is no there is no interaction of the disk's gravity to all the yeah, exactly. If we consider the disk gravity, that will give you another gravitational component. Yeah. So, but in this case, the theory kind of agree with where the simulation agrees with where we say it should break. So we try to apply this to these systems, but it seems it's really difficult. One reason is this unknown inner boundary condition. So where the inner boundary is, this disk breaking is very sensitive on where the disk's inner boundary is. And in observation, we actually don't know where this inner boundary is. So we can find the model which works so that the binary will break, the disk rings free, but we don't know if that's the real case or not. Okay. So so far, I talk about protoplanetary disks. We have seen these broken disks. Yes. Yeah.
So in the first simulation for orbit, you showed that it was a high viscosity. There were no breaks, but then you didn't talk about viscosity.
Yeah. So here is those are all low viscosity case. If you have high viscosity, it may not break. The reason is the inner disk. Normally, you think okay, the high viscosity. The reason not breaking is because they are connecting an inner and outer disk by viscosity. But in the simulation, it's not that simple. What happened is that the inner disk will start to align with the binary plane. So when they align, then you don't have the tear. So when they're aligned, then the precision will not cause this. There is no precision. When there is no tear, you could have a warp, but the warp won't break. So when they have a high viscosity, is that you quickly damp the precision to make it align, and then you develop steady warp, but there is no precision, so it will not break free. Yeah, so this is another finding in these simulations for viscous disks. It's very different from traditionally disk breaking condition for viscous disks. Is that we think the disk alignment is more important than this the wave communication for viscosity. Yeah, but that also suggests if this mechanism works, the disk viscosity is very low. Yeah, so far I have described how the companion, misaligned companion, will affect the disk to make the disk break. On the other hand, every interaction has two sides. Right? You will have a companion affect the disk. You could also have the disk affect the companion, and this maybe have applications to stars and black holes in AGN disks. So imagine you have a misaligned companion, and now the companion is low mass. It's not high mass companion which can open gap and warp and complicate stuff. It's like a low mass companion, and low mass companion will pass through the disk. It will move from above the disk to below the disk. So it will travel across the disk. So if we zoom in this region where the companion is moving across the disk, you see this is a companion's Capillary speed going up to lower right. But the disk is also rotating. The disk have a Capillary rotation moving from left to right. So the relative speed between the companion and the disk is actually in this direction. So from the disk perspective, if you stand on the disk, what you will see is that you will see the companion actually moving from upper right to lower left, not in this direction. Okay. So if you see for the disk, if you have a companion moving through the disk, then you will feel aerodynamic drag. The star, for star, you will feel aerodynamic drag. It's the same way as you drive a car in the highway, you feel aerodynamic drag. For black hole, the black hole is a lot smaller, so the aerodynamic drag is weaker. But the black hole has very strong gravity, so it will cause this Mach-Cohn wake. They will gravitationally interact with the black hole, and this is dynamic friction. But nevertheless, you will feel a force. You will have a force which is opposite to the relative motion. So this companion will feel a force pointing upward, like here. Okay. And if you consider how this force will tilt the orbit of the low mass companion, if you do like R, F, right? If you L here, then you will change the L to this direction. So this has two effects. The first is for a misaligned companion, the orbit will quickly shrink. And the second is that this orbit will start to align with the disk and eventually be embedded in the disk in the same direction. This is very extreme if this companion's orbit is retrograde. So imagine the companion is almost retrograde. So the orbit is almost flipped. Okay. And this interaction will cause the retrograde orbit to go to 90 degrees and then finally coplanar. Okay. So the retrograde orbit will not just sink into the disk retrograde. It will actually flip all the way to become coplanar. Okay. So this effect will cause this fast migration and inclination damping. So imagine if we have a nuclear cluster at the center of the Milky Way, then this is the image for our Milky Way center. And all the stars in nuclear cluster, the total mass is actually larger than supermassive black hole mass at the center. And sometimes you could have AGN phase of the nuclear of the central massive black hole. So the central massive black hole start to accrete fast and forms the AGN disks around the supermassive black hole. For Milky Way, we have seen these Fermi bubbles, these gamma ray bubbles, indicating there were past accretion disk activity in our central massive black hole. So if you put these two together, if you have nuclear cluster and a supermassive black hole is undergoing accretion, and you have accretion disks, and then all of these misaligned orbits, stars and a black hole will interact with this disk, and their orbit will start to shrink and align. Okay. So this is work done by a postdoc at UNB, excellent postdoc, Zhaohuan Wang. So he calculates if you have stars or black holes in this picture, what's the time scale for them to drift, this migration and eccentricity damping, and how fast they will become polar, they will be aligned with the disks. So overall, the migration time scale and eccentricity damping time scale is shorter than the inclination damping time scale. So in other words, all of these stars, they will quickly drift in the disks, and then they become circular, and then they will sink into the disk. And one important integral constant he found is this integral motion, is the angular momentum of the companion times cosine I over 2 square is a constant. So with this constant, you could connect the companion's initial semi-major axis with the companion's final semi-major axis. So this is a constant during the companion's orbit or sinking to the center. Okay. So you could work out that if the inclination of the orbit is very high, for example, if the orbit is almost perfectly 180 degree, almost retrograde, then I naught is 180 over 2 is 90, cosine 90 is 0. So that means for very inclined orbits, when they sink into the disk, their orbit could shrink by order of magnitude. Okay. So this has implications on tidal disruption event. For example, if we have a retrograde star in an AGN disk, they will shrink and tidally destroy. If you have a slightly retrograde, but not perfect in the disk plane, while the orbit trying to go into the disks, they will like shrink and tidally destroy. And if you have orbit this, they will go to the 90 degree and prograde and destroy. Okay, so all of the orbits in this range will be tidally destroyed. Only the ones orbit misaligned in this range will eventually align captured by the disk. So given a nuclear cluster density model, density and massive AGN disk, you could calculate how fast these stars will be tidally destroyed by the black hole in this picture. So this dashed curve is the normal relaxation TDE rate. You have around 10 to the 4. And this is the disk capture TDE rate during the AGN phase. So you could increase the tidal destruction rate for stars by 1 to 2 order of magnitude here. So during the AGN phase, the TDA rate could significantly increase due to this AGN disk nuclear cluster interaction. And this may explain a lot of AGNs which change their look during the AGN phase. Like here, you have a IPTF, suddenly becomes like a quasar with the borderlines in a year's time scale. So it could be one of these disk captured TD. Okay. So we could also calculate how many stars and black holes will be captured in these disks. We could calculate how closely these stars or black holes packed. So this is a number of objects within Hill radii. So when this number is close to 2, then you could form binaries directly in the disks. You have these 2 stars very close to each other and form binaries. So overall, if the AGN phase is long enough, all the nuclear stars in all the stars in nuclear star cluster will sink into the AGN disk, and they will be close packed, and they will be close enough to be binaries. So this could be the direct disk captured binary for both stars and black holes. So stars and black holes are so packed in the AGN disks, and direct binary formation is actually possible with the right condition. Okay. So to summarize, we have seen these companion disk systems across all the scales, from Saturn's ring system moons to protoplanetary disks, planets in protoplanetary, to stars in AGN disks. They share a lot of similar physics. Recent observations in protoplanetary disks start to drive us to think about misaligned companion in disks. And this misaligned companion could break the disks. And they could also, if it's a circumbinary star, they could torque the disk and break the disk. So there are several mechanisms you could break the disk. But you could use the information of these shadows, and these things could constrain the companion mass. So finally, if we apply some of this theory to stars and black holes in AGN disks, you will find that some of AGN, all the stars in nuclear star cluster could flip their orbits by interacting with the AGN. While they are doing so, their orbit could shrink dramatically. So you could have this disk captured tidal destruction event, maybe related to changing of AGN. And when a lot of these black holes and stars sink into the AGN disks, you may be able to form these binary black holes directly. So that's all. Thank you.
binary block both case, so there should be a delay time
Hmm.
from formation to merger.
Yeah,
So the merger typically happen when the black hole is still an AGN or
yeah. So here is just like when the things we calculate when things get close to the Hill radii in the orbit. So they could be captured, but this is far away from where they will like really merge. And this is like 4 or 5 order magnitude from the like Hill radii all the way to the gravitational radiation. So how you could go through this process could take a long time. But there were theory with the disk assistant merger. If you have this binary in a disk, that could drive the binary orbit to shrink. But it related to the binary orbit orientation. I think it's retrograde binary is easier to shrink. If appropriate, it's harder. So it's unclear how these binaries will eventually actually collide, even when you have gas peak so long. So all of these binary black hole forms, how they become GR source, probably could take a long time. If they form in the retrograde orbit, they may shrink very quick. And maybe during AGN phase, you may see gravitational wave. But if they are prograde, they may last forever with these boosts.
So how do we excite inclination in protoplanetary?
In the first place, yeah. So here we just put like, say if you have inclined planets, and there are various ways you could excite the planets to high orbit. Yeah, there are resonances like scattering. So when you consider the disk's mass and the precision when the frequency match, you could like scatter coming out. Or you could have like a secondary forming disk. You have a first generation disk, you form planets. And then you have secondary infall, late infall, they form a disk which is misaligned with where the original disk is, and you have a significant misaligned. Yeah, so how you have a planet misaligned? Yeah, that's a good question.
I have two. Well, thanks for the nice talk. I'm just curious about two tiny points. The first for the changing look AGN case, is that the collective spiral shocks excited by this big star interaction changing the accretion rate to change the velocity, or just collect all those enhanced TDE and sum their total accretion rate together, and they're going to outshine the AGN?
Yeah, so you mean the after the tidal disruption event, how it changes the AGN accretion rate?
I guess so. It's like in some sense, you could imagine one case is because there's so many interactions of this changed orbit, it just excites spiral shock waves in the disk. But for that to happen, I imagine it has to be some sort of very efficient angle moment to the moon.
Yeah.
In other case, it could be like TD happens so frequently that you just at a short time you sum all these TD together and they change the like the accretions from TD not changing the original.
Right. So what we thought is could be is the TDE changes the AGN hook. This tidal disruption event is different from this parabolic tidal disruption because they first shrink and then circularize. So it's almost in a low eccentricity orbit and gradually gets to the tidal disruption radius. So it's this gradual like process gets to the tidal disruption radius. So unlike the normal TDs of like parabolic pass by and generate these streams, this one maybe is like a slow process. You could deform the star and get rid of the star envelope, remove the envelope material and form these. We don't know exactly. We haven't done hydro simulation. This is just based on the dynamic calculation, how the orbit will change if you interact with AGN. But the bottom line here is that the eccentricity damping time scale is smaller than the inclination damping scale. So it will be very quickly circularized, even if initially it's very high eccentricity, but it will very quickly circularize. And then they have this slow process to gradually move to tidal disruption radii. So the signature of this tidal disruption could be very different from the normal TDE because you have it's like the circle is like a low eccentric version of that normal mean. We don't know exactly how it works.
But it's interesting extrapolation to normal TDEs.
Yeah.
I guess I have another quick question. Like for the disk breaking case, will there be a condition for the Mach number of the disk, or like I think there's an output disk, or they're gonna just maintain whatever Mach number before breaking?
You mean the
Or like scale height,
you mean the temperature? You change the Mach number?
or like a scale height of the disk after breaking, or they just maintain like roughly?
Yeah, the disk is roughly maintained after it breaks. The disk quickly communicate within the region, communicate and become two independent rings, and each one is still vertical hydrostatic equilibrium. So it's just two disks misaligned. So the thickness is not changed.
Very nice talk. I have a question about the physics that you're including in the models of the disk.
Yeah.
Because the protoplanetary disk is a very rich physics. It's like all effects and
Non-isotropic
isotropic transport, depending on whether you're in the midplane or further
Yeah.
out, or you're kind of going further out in this. Like, does it affect the disk breaking and changing perspective? Like, depending on what you include, or is it all?
Yeah, so here, yeah, so we simplify this in when we talk about breaking, we basically say it's invasive disks. So protoplanetary disk turbulence level is very low. So we say it's invasive, then it's all about the sound wave propagation, communication. We haven't talked about the magnetic fields, really connect different parts and have magnetic torque. Tomorrow in link school, I'll talk about MHD effect. So that will be much more complicated. The viscosity will not be isotropic. Also, if you have hole, then you have hole here and yeah.
Following up on what you said about the origin of the misalignment, how common is that? Is it a small fraction of protoplanetary disks that have a misalignment?
Oh, it's actually for a lot of these very large disks, protoplanetary disks, a large fraction are actually misaligned. So there is especially around the Herbig AEB star, around the massive stars, these are transitional disks around massive stars. So a lot of them show shadows, meaning that the disk is misaligned. So something is very different between these massive stars and the low mass Taurus star. We don't see much disk breaking or shadow, but for the disk around these high mass stars, a lot of them you see the misalignment. Yeah, a high fraction. And the misalignment normally accompanied with a spiral, accompanied with a non-symmetric structure. So it means there is something very dynamical process, very dynamically going on.
Is there a disk mass limit when this is true?
Oh,
Is there a minimum mass above which that statement is true? The fraction is high, right? For low disk masses.
No, it's
you don't really see the scattered light.
Yeah, for disk around T-Tauri stars, I don't think people have seen misalignment. For the disk around Herbig AEB stars, they see a lot of a significant fraction of them misaligned. The scatter light, because could trace a tiny bit of dust in the disk. So I don't think there is any constraint on the disk mass, how large the disk mass. Yeah, I don't know exactly the number.
So just following up on that, could that be an effect of binaries, the low mass T-Tauri?
Yeah, right.
Rarely in binaries.
Yeah, exactly.
Where high mass stars are
Yeah, exactly. That's a natural explanation why you have the higher Herbig AEB star, because they have higher fraction of the. Right? But people search very hard for these. And so far, only in one system you find a binary, which the first system I showed, the so-called binary disk. You see the other ones. People haven't found any binary in the system. I mean, that should be the natural explanation.
Does the thickness of the disk and the ratio of the thickness of the disk and the planetary radius or the companion radius matter when you accept those like density waves?
Yeah.
Because I think if the ratio is very small, and then you have something like Saturn's ring, right?
Yeah.
The ratio is large, perhaps it's more similar to
Yeah. So the disk thickness is another parameter. In protoplanetary disk, this thickness to the semi-magnetic axis ratio is around 0.1. But in AGN disk, depends on which AGN disk model you use. Some can go to 10 to the -3. So there is of course, huge uncertainty in AGN disk models. But if it's 10 to the -3, that means even a 10th Earth mass black hole could open a gap in AGN disks around like supermassive black hole. So you could think about gap opening in like AGN disks. Yeah. But the theory is that you could scale the theory to any number. But AGN disks could potentially be very different from protoplanetary.